Thanks. If you're having trouble with your Wi-Fi, imagine how I felt about an hour ago when I found out that Reveal.js and Jupyter Notebook slides require Wi-Fi to download the CSS and JavaScript that makes them work. I was kind of panicking. But they work. I was able to download the files and get it running locally. So pro tip, if you're going to use Reveal, be aware of that. All right, so yeah, this is a bit loud. Let me see if I can turn this down a little bit. Excuse me. Yep, so I'm going to talk about, I tried to put as many buzzwords in my title as I possibly could. I'm going to talk about basically combining 3 open source technologies, which, to be clear, I had basically nothing to do with, to implement a machine learning workflow. And the 3 things I'm going to combine here are custom machine learning, and for that I'm going to use TensorFlow. And I'm going to use a standard interface for machine learning so that I can, what I come out with, what the TensorFlow model that I have, I can use an existing, existing workflows that we have and compare and easily swap in with other machine learning algorithms. And then finally, a simple distributed computing library called joblib, which is actually integrated in scikit-learn, but it provides some functionality to let you implement custom backends so that you can distribute processing according to however your stack is set up. Okay, so so I realized last night that I have a little bit too much content here, so I'm going to go through pretty quickly. So first, custom machine learning. It's been really amazing how much easier machine learning implementation has gotten over the past few years. It's getting almost to the point where it's like just writing equations on the whiteboard, and then you have sort of this very scalable, reliable, fast implementation. I'll talk a little bit about TensorFlow and Theano and things like that and why they are useful to start with. Kind of give some background, give some motivation. To be clear, the focus in this talk is supervised discriminative machine learning with gradient-based optimization. This is used for deep learning, also sort of just logistic regression or linear regression, ridge regression, things like that would also fall into this category. There are, of course, other types of machine learning. There are tree ensembles, there are probabilistic graphical models. There are also some very interesting tools sort of analogous to TensorFlow for graphical models, things like PyMC3 and Stan. If you're not aware of those, I would recommend checking them out. But TensorFlow sort of provides facilities to implement supervised discriminative machine learning models, among other things. So with discriminative machine learning, we're trying to find a function. So this is a little bit maybe elementary, but I just kind of want to get everybody on the same page when I'm talking about TensorFlow. So we want to find a function that will output some y, some label, or some target value, given some features x and some parameters w. And finding those right parameters for our model is the goal in the machine learning, the algorithm. So for example, the features could be counts of words in a movie review, and then maybe the output labels would be, or the targets would be positive, negative sentiment, whether it was like a good review or a bad review. So typically a way to solve this problem, to find a good function, prediction function, is to use gradient-based optimization. This is sort of the standard technique with deep learning and neural networks. And so it sort of consists of, at a high level, 3 steps. First, we define our objective function, call it g here. That takes some training data, x and y, and then also we want to, sorry, I feel like this is a little bit too loud still. Move it further. Our goal is to find a setting for the weight w that sort of optimizes g. So this would be like, so it could be like minimizing some loss function or maximizing some probability or score. And often this is, g is defined as sort of a difference between the predictions that the prediction function currently gives and the true targets that we have in our training data. So the second step is to then take that function, and then for the machine learning algorithm, we need to take steps towards finding the optimum. And so for that, we'll typically find a derivative of g with respect to w, so we know which direction to take our steps. And so this is actually really painful without something like TensorFlow, because you basically have to implement your objective function, and then you also have to implement your gradient, and there's basically sort of separate things. And also sometimes the gradient can be much more complicated. And then once you've done your gradient, you iterate, you compute the derivative, you update W, you iteratively do that until you reach convergence or until you get tired of doing it. Or how that validation goes indicates that you should stop. So TensorFlow and more generally graph-based numerical computation methods like it, including Theano, sort of really help this process, because for step one, the sort of implementation of the objective function, that becomes much easier because it's sort of a standard interface and tools for a lot of the different functions you would want to do, like softmax or a sigmoid function. All the matrix multiplication things become much easier. Step two becomes actually, which was very hard before, becomes one line of code. Literally, you say TensorFlow.gradients, and then the inputs and the output and what you want to take the gradient with respect to. And then step three also becomes maybe one or a few lines of code, because TensorFlow and other tools like it have learning algorithms, these gradient-based learning algorithms already built in. So, sorry, I'm sort of proselytizing TensorFlow here a little bit. But, so yeah, TensorFlow, it's developed by Google. It's an open source project, very popular, has kind of weirdly has more stars than scikit-learn, I think, on GitHub. But as I mentioned, there's alternative tools, in particular Theano. There's Keras, which is a nice very nice wrapper for both TensorFlow and Theano. And then a bunch of other things. They get released like all the time, I feel like. So probably there's some that have been released since I started this talk. So if you went yesterday to Joel's talk about FizzBuzz and TensorFlow, you probably already got a little bit of this, but I'm going to go through it again real quickly. So sort of brief introduction of what TensorFlow is and the different concepts, core concepts here. So there's variables, operations, graphs, and sessions. So what you do in TensorFlow to define your prediction function or your objective function, you're constructing a graph where you have inputs, and then you're multiplying things together, and you have your weights and your variables that you want to optimize, and then finally at the top you would have your objective function. So you're defining this graph. So first you instantiate one of those, and then as sort of a convenience thing, instead of having to do like graph.add every time you want to add something to your graph, TensorFlow has this nice sort of context management. There's also a default graph, but unless you want to have a global variable, it's probably desirable to use the context manager. And then you define placeholders, which would be inputs. So this would be like, for example, features that your model would make predictions about. Oh yeah, and this example here is just a really stupid, simple example where it's just there's a variable that's a sum of things, and that's just adding things into that. So we have the placeholder, which is what we're going to add. We'll have some variable, which will store a state. In machine learning, this would actually be like a weight or parameter for a variable. And then we have to have an operation to initialize the variables. Here we said that we want to initialize with 0, but we could also initialize randomly for a neural network, for example. And then we'll have another operation to do things. We'll add operations for actually doing the work that we want. In this case, we're just going to add the sum, add the input to the sum, and then assign it to the sum. So we're just incrementing sort of here by the input. And then there's also a session, and so there's this. It's a little bit maybe not the most intuitive thing in the world, but sessions. I sort of think of it as rough analogy, but I think of a graph as sort of like an executable in Unix, and then a session is a little bit like a process where it has it has the state. So it's maintaining state for these variables. So the graphs is sort of describes how the processing works, but then when it's actually running, the session sort of manages that. So, and then you can run multiple commands within a session, so you can check the initial value, and then you can add things to it, add a few different vectors of input, and you see, you'll get the outputs. Another point is if you make another session, then you've lost all those values, and you start back at the initial value. By the way, I'll tweet these slides later so people can take a look in more detail. So as I mentioned before, TensorFlow provides this automatic differentiation magic, which is amazing. So basically every node in that graph, it knows how to differentiate it, and then it can just sort of propagate down the graph. But so, if you define a simple function, then you can take the gradient of it. Just make sure I'm actually highlighting these things on screen. If you take the gradient of it, that's just one line, and then you have your gradient. And then you can run it and get your gradient of things. Right, so that's very easy. So, okay, that's the TensorFlow introduction. Next, I'm going to talk a little bit about multi-layer perceptrons, which is the sort of framework I'm going to move forward with for the rest of the talk. So this is a very, very sort of simple, basic, sort of the core sort of first neural network people think about. It's a feed-forward neural network. That means there's basically no recursion in it, and also there's no convolutions as you would see in an image processing network. So basically what we have is an input layer and one or more hidden layers, and then an output layer. And the nice thing is, unlike a linear model where you would just have basically an input layer and an output layer, you can model interactions between features, so complex relationships. And in fact, if you have one layer, I believe there's this thing called the universal approximation theorem that says you can approximate any function as long as that layer's wide enough. So multi-layer perceptrons are not something new, they're not something fancy. It's actually quite an old idea, but the nice thing is that it sort of combines with all the state-of-the-art neural network methods. So you can use ReLU activation functions and dropout, which is kind of like regularization, and then all the latest sort of gradient-based optimization techniques. Oh no, yeah, that's not good. I had a diagram. And now the battery's out. There we go. So I had a diagram. I don't know where it went. I blame Wi-Fi. Although it's local, so it's my fault. There's an input layer. I had a diagram with an input layer, a hidden layer, and then an output layer. But basically a multi-layer perceptron is like this. You're trying to make some prediction of a target Y. And yeah, I'm just going to skip this slide, actually. But then the thing I wanted to point out here is there's this, the first two layers are going to be the same for a lot of different models. So if you're doing classification, the first two layers are the same as if you're doing regression with the multi-layer perceptron. The only difference there would be the output function and the output layer and the objective function that you're going to maximize or minimize. Right, so I'll talk a bit about how I implemented this, but first I want to go on and talk about scikit-learn a little bit. So TensorFlow gives you the ability to implement custom machine learning models, but it's might not fit in. It doesn't immediately fit into sort of a scikit-learn framework that we sort of all know and love. And it doesn't. You can sort of do whatever you want. Define your own API. But it's kind of nice to have sort of a standard API to work with, so that it can you could swap in the multi-layer perceptron and swap in a gradient boosting, or swap in a logistic regression, and try a whole bunch of all the different things that scikit-learn provides. And so I wanted to implement this following this standard scikit-learn API. This is, of course, as I said, not built by me, but it's a very, very nice, consistent API that makes swapping in different machine learning algorithms, trying different things very easy. They all follow a very standard interface. There's helper functions, which help you with your things like input validation, pre-processing, testing. There's also a talk yesterday by Tom about implementing a transformer, which is very similar, but here I'm going to be implementing a predictor. Particular classifier and regressors here. And another very important part of this is that there's some very nice functionality to actually check that what you're implementing follows the actual API. So they have a whole suite of tests, unit tests that will run on your custom estimator to make sure that it actually is a custom scikit-learn estimator and not just some piece of code. Yeah, another thing that scikit-learn makes easy is grid search over hyperparameters, which I'll talk a little bit about. But to implement a scikit-learn predictive model, what we need to do is implement fit and predict methods. Those are the two key things. You can also, if it's a probabilistic model, or if it can give you probabilities as predictions, you can implement predict proba. The init function just needs to attach arguments. It's a little strange, and actually, like your editors may complain because Python, you're normally supposed to attach define all the member variables in the init function, I believe. But a lot of the work that init does actually is done in the fit method once you have the training data that you're going to do, that you're going to use to train the model with. And then fit also usually attaches some instance attributes, such as for logistic regression, you get a coefficient matrix. Everything should be serializable with pickle, and then there's also some nice mix-ins with this that we'll use. Okay, so yeah, I implemented a multi-layer perceptron using TensorFlow and set it up to follow the scikit-learn API. Has some nice features. We get GPU support for free through TensorFlow. Can take in sparse or dense matrices, which is slightly tricky with TensorFlow. Yeah, there's a generic base class. As I mentioned, the first two layers are the same, regardless of whether you're doing regression or classification. So a lot of that code doesn't have or can be reused. And because I'm really bad at naming, I called it a multi-layer feed-forward neural network. Called it Muffin. It's on the GitHub. I'm not trying to claim that this is the best thing in the world. There are alternative approaches you could take. In particular, scikit-learn has an MLP classifier. It uses a CPU. There's a TensorFlow Learn, a contrib package that's being developed that has some similar things. Also, maybe some little bit maybe better out-of-core learning support, but maybe not as good of matching the scikit-learn API. And then there's also Curis, which is very nice, which provides some functionality to wrap models, deep learning models, in something that looks like scikit-learn API. But let me talk a little bit about this. I'm going to go through this real quick. So what this looks like, so this is the base class that sort of implements the first two hidden layers and provides abstract methods for implementing the output layer and the objective function that you want to optimize in your model. So as I said, it imports some scikit-learn, imports the base estimator from scikit-learn. Extends that, subclasses it. And then the main thing is the fit method. And as I noted before in my introduction to TensorFlow, we need to define a graph that we're going to add all the operations to and the variables, our weights, our inputs, all the layers of the network. I'll have this on the next slide, but we're going to initialize a model here. And then we'll also have a session. So when we're training the model, we will store the values of our weights in the network. And then we'll do learning down here. We'll go through a number of iterations through the training data, and we'll part of this will have the learning algorithm that will we'll be running updates down here where we pass in the mini batches of the training examples. So there's some abstract methods we need to implement, but the core modeling code looks like this. So this is the actual TensorFlow part of implementing a multi-layer perceptron. So dropout is this sort of it's like regularization, sort of a probability of dropping inputs in the network as we're training. And so we have a value for a placeholder to be able to turn that off, because you actually want to turn that off when you're making predictions. So we have a placeholder for that as an input, and then we also have the input layer here, And then the class takes a hidden units keyword argument, which defines how many layers in your network there are and how large each of those layers is. So it takes a list of integers. So if you had 256, 256, 256, you would have 3 layers with 256 units each. So we'll iterate over those values and add layers for each one of them. And then we'll initialize our objective function, which depends on the initialize our output in our objective function, which depends on the particular, whether it's classification or regression. And then we'll define our learning algorithm. And as I mentioned, TensorFlow has some nice, sort of all the latest learning algorithms, or most of the latest learning algorithms implemented already. And you can very easily set up your training. Yeah, so one problem is TensorFlow doesn't pickle very well. So this, and maybe there's a better way around this, but has sort of implement what I would like to call a hack. So TensorFlow has a saver class, but as far as I can tell, it can only write to disk. But thankfully, you can override a getState method in Python objects that Pickle uses when it's trying to save something. So what I actually end up doing is writing the model to disk, reading in as bytes, and then pickling those bytes, and then undoing that when you want to load it back in. So some kind of crazy. I'm just going to skip over that code for the interest of time. Not that typical. So here's what the subclass looks. Sorry, here's what the classifier subclass looks like. As I said, we need to implement our model output, and here it's going to depend on whether we're doing multi-label classification, multi-class classification, or binary classification. I could have actually implemented these as 3 different subclasses, but I chose to sort of follow what scikit-learn already had for random forests, where they implement these 3 things in the classifier. So we have different, a little bit of control flow statements here to decide what type of model we're doing. But then at the end, we define our output layer. And we also have a function to initialize our objective function to define what that should be for our model. And here for a binary classification, it would be a sigmoid cross entropy between the predictions and the input, or sorry, the target labels in our training data. And yeah, it's important to note that TensorFlow provides this for you. You don't have to define it for yourself because it's a very standard method for deep learning. And then there's a little bit of logic in predict and predict proba. Those are pretty easy to implement. So, third part of the talk, simple distributed computing. So an issue with deep learning is all these layers, all these neurons, lots of matrices and tensors, whatever, flowing around. It can get kind of slow. So, and also there's all these hyperparameters, like whether you're using dropout, what the dropout value should be, how many layers you're using, what size of those layers. Very large space. It's very similar to like gradient boosting, where you have all these parameters related to how many, the depth of the trees and things like that. And so you sort of want to explore the space and try a lot of them on your training data with cross-validation before you sort of pick what the proper setting should be and train the final model. Yeah, the typical sort of standard way to do this is grid search with k-fold cross-validation on the training data. This is sort of a crude method. It's basically brute forcing the solution, trying a bunch of points on a grid. But the nice thing is it's embarrassingly parallel because one grid point doesn't depend on the model training on one grid point doesn't depend on the model training on the other grid point. So we can very, very easily parallelize this, where we just run all the grid points in parallel and then at the end find out which one was best. There's alternative hyperparameter search methods. They're also parallelizable to some extent. It's worth mentioning. Yeah, so I just ran on the scikit-learn digits dataset with logistic regression just to show you that this is actually important. But this is probably pretty well known here. But like the default value would be this, and then you can do about 10% better if you do some tuning. And with deep learning, this would be more pronounced. So you'd get a totally useless model if you pick the wrong parameters, or a really good one. So for this, we'll use joblib. This is a Python package for running these sorts of embarrassingly parallel tasks. Again, not developed on me. It was originally, I believe, focused just on single machine parallelization because there are backends for multiprocessing, multi-threading. So here's a simple, actually I'm just going to skip this in the interest of time, but it's very easy to use, so you can define a function and then you can parallelize it, and that'll run on, in this little bit of code will run on in multiple processes and compute each of these numbers separately on a separate process. So a key thing is scikit-learn actually uses joblib in the grid search CV. So if you set the number of jobs parameter other than which defaults to 1, if you set it to 10, it will use 10 processes. And also, if you tell joblib before doing the grid search, if you tell joblib to use a custom backend that you've implemented, then scikit-learn will use that custom backend, that custom joblib backend for grid search. And so I'll show you what that looks like later. But yeah, so as I mentioned, joblib was sort of originally just multiprocessing, multi-threading, I believe, but now it has support for custom parallel backends, has a nice API for that. So an example, this has a DAS distributed backend. There might be one for Spark or something, I don't know. But to implement one of these, you have to implement two things. You have to implement a class representing a pending result, so something representing something, a task running on a separate machine or a separate process or separate thread. This is basically very similar to a concurrent future. There's a get method which will retrieve, which will block and wait for the result, and then there's a result attribute which will just cache the result. And then you have to implement the backend base subclass. So you have to subclass this parallel backend base. Note it's actually in a private method, but there's an issue to make that public because there's no reason why it shouldn't be public. Basically, all you have to do here is apply a sync method, which will take a function that you want to run and queue it up for computation, get it started, and then return one of these pending result instances. So Civis, we have our own custom or our own auto-scaling EC2, Amazon EC2 Docker-based system for running jobs in the cloud. There are all the other systems, you know, Kubernetes and Mesos, things like that. You probably do the sort of thing with. But for the purpose of the talk, I'm just going to talk about our. Well, I'm going to just use our infrastructure. I'm not really going to talk too much about it. But so we wanted to implement the joblib custom backend for our infrastructure. We actually already had a concurrent futures executor subclass or interface to our system, which will allow us to sort of easily submit commands to and run things on Docker containers. And we'll use joblib to make this easier to work with scikit-learn. So I think in the interest of time, I will skip this as well, but just sort of an outline of our, or mostly skip it, an outline of our backend. And so as I said, we have to implement the async method and then also this result. Okay, so I just want to wrap up with sort of a real basic evaluation just to show you not whether it's the best thing in the world, but you know, does it work? Okay, so first I'm just going to compare multi-layer perceptron to just logistic regression for a text classification task. Look at model accuracy there. And then the second step is I'll compare grid searching on my laptop to grid searching in the cloud in terms of just how long it takes. Okay, so setup of the evaluation for text classification. There's a nice movie reviews data set from an ACL paper several years ago. It has a couple thousand movie reviews with positive and negative sentiment labels. It's a fun data set. And the features here for our models are going to be just character engrams. These are just going to come from scikit-learn's count vectorizer method. And this is actually a pretty good NLP. My background's mostly in NLP, but this is actually a pretty strong baseline, I think. Our evaluation setup is a little bit different from the original paper, but we're going to randomly split the reviews into training and testing sets, and then we're going to do hyperparameter grid search on the training set, and then we're going to evaluate the final model that we get out of the grid search using AUC score for testing set predictions. We've got to import some stuff. So NLTK, the package NLTK provides the movie reviews sort of pre-parsed and ready to go. Very easy to set up the data set that way. So here's how we're going to implement the experiment. Very, very simple once we have all these things put together. We have our count vectorizer, which will take text, which will take text as input and output let's see, yeah, matrices with indicators for particular character engrams. So it'll be a very sparse matrix. And here it will actually extract all the engrams. Sorry, engram would be a subsequence of, well, in this case for character engrams, so it's a subsequence of contiguous characters in the input. So, you know, little word fragments and spaces between words and things like that. So we'll go from 2 characters in a row all the way to 5 characters in a row. So it'll extract all those features. Very, very sort of simple, knowledge-free, very no linguistic knowledge here. Then we will instantiate our multi-layer perceptron classifier. We'll throw that into a scikit-learn pipeline. And in order to grid search, we'll define a parameter grid. Here we'll do a very, very simple parameter grid. We're just going to explore a network with one hidden layer of 512 units, and then another network with one hidden layer of 256 units, and then another network which would be a little bit deeper, where we have 3 hidden layers. In practice, you would probably want to try lots more different configurations of hidden layers. And then also we either turn dropout on or off, sort of the basic 0.5 level. Yeah, and then we'll throw that into a grid search CV. And, oh, I set it here. I set it to use 4 jobs because there's 2 cores and hyperthreading on my laptop. Maybe there's a reason. And then the logistic regression is basically the same thing. Sorry, the microphone just keeps kind of dying here. Not sure why. We'll instantiate the logistic regression class from scikit-learn instead. And then our parameter grid will be slightly different. We'll just tune over the L2 penalty. So then we'll fit those to do our grid search on the training set. And that'll churn away for a little while. And not surprisingly, the logistic regression is much faster. It takes about 4 minutes. The multi-layer perceptron takes almost an hour. In terms of accuracy, the multi-layer perceptron does a little bit better. Nice. A couple points. I don't really know whether this is you know, meaningful, but it's nice to see. It shows that it works. And then we'll do this with our distributed backend, and this becomes very easy. I implemented a class to sort of instantiate one of these backend objects, and then we'll register it. We'll call it the Civis backend, and then to actually run the grid search on that backend, we will use a context manager that joblib provides, and then anything happening with the joblib within this context will use our custom backend. So when scikit-learn's grid search CV wants to fit and score models, it will do that using our distributed EC2 base our infrastructure. And it's faster. It's not like magically faster, but it's quite a bit faster, going from an hour to 15 minutes. An important thing here is it's actually, once it's done doing the grid search, this also includes fitting the final model that did best in the grid search on my laptop. Right, so that's pretty much it. But just some parting thoughts. These are kind of speculation. Don't have a ton of evidence to back up these assertions, but with deep learning, hyperparameter search and speeding up is really, 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 really important. It's kind of the key to getting it to work. And so, you know, the fact that Google is doing really well at this is not surprising because they have all the infrastructure to do this hyperparameter search. And my opinion is that for most people, for most applications, doing that, figuring out how to do the very simple, easily parallelizable distributed grid search is probably more important than figuring out a more complicated sort of process of how to distribute the actual model fitting procedure, which is another thing that machine learning researchers are actively investigating. So if you have like really, really giant like click-through data or something where you have like trillions of instances to train on, then maybe distributed model fitting would be really, really important. But for most models, gradient boosting on medium-sized data sets, or deep learning on medium-sized data sets, the distributing that grid search is going to be really, really helpful. And then final point, with combining these tools, it's, you combine three things, but, the whole is greater than the sum of its parts. Thanks for people who did code review, contributed to the project. I'm told we have 5 minutes. Yeah. So there are different methods where. Oh, sorry. I knew I was going to forget that. I was like, repeat the question. And I forgot. Yeah. So the question was basically this brute force grid search is really expensive, and there's got to be a better way. Yeah. So yeah, I think there are methods. This is really an active learning area of research, and there are methods even in I think scikit-learn has a couple options to do these things. My impression right now is that they most of the time they'll work, but then sometimes they won't, and most of the time they'll work a little bit better than grid search probably, but then sometimes maybe they won't work at all or they'll kind of screw up. So I don't particularly trust them. I think maybe a couple more years this will be something that people have figured out. But I think it will still be computationally expensive. The space of parameters, so if you imagine sort of as this multi-dimensional function, you're trying to sort of optimize that function. And most machine learning models are at least locally convex, and kind of smooth, whereas this hyperparameter space has all these different things, like for gradient boosting or something, you have a number of trees, and then how to split the trees and the splitting criteria and all these different things. Learning rate, and all these things are very different, and so that space is really not as smooth and easy to search around in, and so that's part of the reason why people use grid search. People are looking into Bayesian methods to sort of priors and this mic really is weird. Bayesian methods for doing that, and then just there's hyperopt. There's a thing called hyperopt that people use sometimes. So I think that this will be a really, really active and important learning area of research. But it will still require or benefit from parallelization, I think. Any other questions? I think this thing is out of battery. It's Heilman 13. I'm still new to the Reveal.js. Wow, there's a lot of slides. Yeah, there is. Any other questions? Thank you.